today I'm going to cover a few of the lectures I have to study, and this one that I'm going to begin with is about antibiotics. Very, very useful things. As you'll know, when you get sick and a bacterium infects you, you take antibiotics to defend against it. That is because antibiotics are chemicals synthesized by organisms that inhibit the growth of other organisms. And to be useful, the antibiotic must have selective toxicity, which means it should let one organism grow, which is us, humans. It can't kill us, otherwise it's not good for us. But it needs to prevent the growth of other organisms, such as the bacteria that infects us. And to be selective, the antibiotic must target specialized functions in a cell. Alright, the organism of the week is Streptomyces coelicolor, and this was initially mistaken for a eukaryotic fungus because of the way it appears. Actually, the way it looks is due to the hyphal grow and not regular cell division. What is special about this bacterium is that it's got a linear chromosome, and there are many different things, I guess, that make this advantageous, but also disadvantageous. So, it's got multiple chromosomes per cell. It does sporulation. It actually grows them in the air, which is a little strange. I think it would be for rapid dispersion if it needs it. And it secretes polyketide antibiotics. Now, I mentioned there were a few problems with having a linear chromosome. That is, you need to have an origin to start dividing, and that would be or C, and division proceeds in the opposite direction. There's a continuous and there's a discontinuous strand. The problem is that in a linear chromosome, the discontinuous strand must be continually reprimed, and there is no DNA template to reprime the termini. So eukaryotes have a solution to this. They use telomerase to extend the 3' termini, whereas Streptomyces have a TPG, or a terminal protein, that covalently fuses to the end of the chromosome, and somehow this fills the DNA gap. Antibiotics that are made by Streptomyces are very, very numerous. I'm going to just mention a few. Let's see, globomycin, bleomycin, ivermectin, never heard of that one, chloramphenicol, streptomycin, erythromycin, vancomycin. 75% of the world's antibiotics actually come from Streptomyces. Each species makes multiple antibiotics, and it makes unique antibiotics. So we like this bacteria. As I said before, Streptomyces specialize in polyketide antibiotics. The polyketides look very complex, but they're actually just variations on one another, and they are related to fatty acid biosynthesis. Okay. Now we're going to talk a little bit about polyketide biosynthesis, and this is where I get a little bit confused, but I will try to make this a little less confused than I think it is. Hi, honey. Oh, my baby's here. Wait, you gotta see this. Kitty. Oh, they're both here. Oh boy, oh boy, oh boy. Guys, play nicely now. Wanna say hi? Wanna say hi? No? Okay. Well, I tried. Anyway, going back to what I was saying. Apparently, genes are like on islands on the chromosome, and they are related. The ones that are related are grouped together, and the synthetase genes are huge, so they take up a lot of space on the chromosome. But polyketide synthase is modular. It's a series of enzymes that are fused together, and there are a bunch of sequential stepwise reactions that occur that manage the assembly line. It's all enzymatic, pretty much. And there's also the way that I said that they're a variation on one another. That happens because synthesis is recombinatorial, so different genes can move around and they can make new antibiotics, but they're based on the same one. So rearranging domains on synthase can produce new antibiotic structures. Pretty neat.